Okay, lesson 6, algebra 2, Euler's number. It is funny. I've always giggled every time I've taught about Euler because it looks like Euler. In fact, every time I first see the lesson, I'm like, oh, we're doing Euler again. Then I remember, no, it's pronounced Euler. Okay, as funny as that is, it's Euler's number. Let's see, Euler, he's a mathematician from Switzerland. He lived in 1707 to 1783. He was a physicist too. He was really smart and he made a lot of important contributions to mathematics, a lot of terminology and notation. He was the one that sort of developed function notation. We thank him for that. He also popularized the use of pi to represent the circumference of a circle divided by its diameter. I was writing it in the denominator, so I got confused. So he really popularized the use of pi to represent that ratio because it is also a irrational number. Euler discovered many properties of the irrational number e. Okay, this is a letter that represents an irrational number, and it's known as Euler's number. It naturally occurs in many applications. Most that I've discovered when doing research into E is interest rates and continuous compounding. In fact, if you do a internet search on Euler's number, you'll find most of the examples talk about interest rates and continuous compounding. We're actually going to talk about cylindrical tanks filling with water to develop Euler's number, not the interest rates. But I want you to see that there's different ways to look it up. So if you do any research on Euler's number, most of the lessons you'll find will develop Euler's number using an interest rate. All right, let's try some exercises. This is sort of, setting the stage for Euler's number. Assume that there is initially 1 centimeter of water in a tank. We're just talking a cylindrical tank, and it's filling, okay? So there's 1 centimeter of water in a tank, and the height of the water doubles every 10 seconds. Write an equation that could be used to calculate the height in function notation of the water in the tank at any time t. This would be an exponential growth problem, and I hope you remember, excuse me, the height of the water at time t can be modeled by 2 raised to the t over 10. And what's not here is a 1, which would be the initial value, the initial start. Okay, it's not written there because it's a 1, but I wanted to make sure that we remember, like, when we do exponential growth modeling, we always have an initial and then the rate of growth raised to an exponent. Okay, so let's now change things around a little bit. What if the initial depth of the tank was 2 centimeters? Well, luckily I pointed out that in that first example, the initial depth was 1, and I wrote the 1 in. So now we can see that it's 2 times 2 raised to the t over 10. If the initial depth was 1/2, you probably already see the pattern. Our initial value is 1/2, and then 2 raised to the t over 10. Initial depth was 10 centimeters. 10 times 2 to the t over 10. The initial depth of the tank was a centimeters for some positive real number a. So a times 2 to the t over 10. H of t. Right? Pretty simple. How would the equation in exercise 2, part D, change if the height tripled every 10 seconds? So we're grabbing this equation, a2 to the t over 10. That's if it doubles. Well, how about if it triples? Okay, so I'm going to go 3t over 10. That's a t. Doubled every 5 seconds. A2 to the t over 5. Ooh, quadrupled every second. Well, A4 raised to the t. Halved every 10 seconds. You're not fooling us. We got this. Halved every 10 seconds. Cool? All right, that was just some groundwork to try to get you sort of thinking in the right scheme of things. Okay, now to get Euler's number, what we're really doing is talking about this tank of water and how it is filling, okay, how it is doubling every however many seconds, how it can be tripling, and what we're going to do is make our interval of time tighter and tighter to try to get our a value from that previous equation as close to 1 as possible. Okay, so we're going to keep messing with our interval of time. We're going to keep taking tighter and tighter slices of time, like 1 second, 1/10 of a second, 100th of a second, 1,000th of a second. So the tighter and tighter intervals we take of time, A will get closer and closer to 1, which is very important, okay? So A is going to get closer to 1, and then our interval raised to an exponent, we'll say b to the r. This is what we need to figure out. It's going to end up being Euler's number. All right, so I hope that makes sense in what I'm trying to do as we do it, because it's sort of difficult. But hopefully I present it in a way that makes sense to you. All right, so back to the slide. Average rate of change, given a function f, whose domain contains the interval of real numbers a and b, and whose range is a subset of the real numbers. The average rate of change on the interval ab is defined by a number. So we have the function at b, so the function evaluated at b minus the function evaluated at a over b minus a. And like I said, our AB, that's going to be time for us. That's what we're doing, is our average rate of change, and we're talking about time. In our interval of time, the distance between A and B is going to get tighter and tighter and tighter as we get closer and closer to A being 1 and developing Euler's number. Cool? All right. So, consider 2 identical water tanks, each of which begins with a height of 1 centimeter and fills with water at a different rate. Which equations can be used to calculate the height of water in each tank at time t? So we're going to use H1 for tank 1 and H2 for tank 2. Here we need our 2 equations. H1 of t equals 2 to the t. H2 of t equals 3 to the t. Okay? If both tanks start filling at the same time, which one fills first? Well, tank 2, because it's tripling, the level is rising more quickly. So we want to know the average rate of change of the height of the water in these tanks over an interval that starts at a fixed time t as they are filling up. Okay, the average rate of change of the height of the water in the tanks. What is the formula for the average rate of change of a function f on interval ab? Well, we just did that previous slide or so. F evaluated at b minus f evaluated at a over b minus a. So what's the formula for the average rate of change of the function h1 on the interval ab? Well, h1 evaluated at b minus h1 evaluated at a over b minus a, duh. Okay, let's calculate the average rate of change of the function h1 for the interval t and t plus 0.1. Okay, that's time, right? So an interval 1/10 of a second long can't possibly time that on your own. So we're doing it mathematically. So our time interval is 1/10 of a second. I'm going to work through this one in detail and then show less and less detail as we calculate more of these. So I've got h1 evaluated at t plus 0.1 minus h1 evaluated at t all over t plus 0.1 minus t. So let's evaluate 2 to the t plus 0.1 minus 2 to the t all over, watch the magic, t minus t, I'm over 0.1, and that's going to happen every time. So I'm not going to do that every time. Okay. Okay, that gives me, remember our exponents? If I'm adding, I'm multiplying. I can factor a 2t out. 2 to 0.1 minus 1 over 0.1. Now algebraically, I can crunch this number. So I'm actually going to move it over here. I have 2 to the t times 0.717735. So that actually equals, because remember, this right here is h1 evaluated at t. 0.717735 h1 of t. Okay, we're going to remember that. That was a lot of work. Okay? All right, let's discuss this answer here. So I have the average rate of change of the height function is a multiple of the value of the function. Let me write that down. So we just did 0.717735 times h1 of t. That's what I said in words right here. The average rate of change of the height function is a multiple of the value of the function. So we just calculated the average rate of change of the height function, but we have the height function in our answer. That means that the speed at which the height is changing at time t depends on the depth of the water at the time. So our depth of the water at the time was 1 centimeter. So let's talk about if we change that at all. On average, over the interval t and t plus 0.1, the water in tank 1 rises at a rate of 0.717735 times h1 of t, centimeters per second, okay? This equation can be used. Let's just play with some numbers. So at time t, there's 5 centimeters in the tank. So we've got 1/10 of a second, the height of the water increases by, okay, 1/10 of a second times 5 times our, I'm missing a word, the multiple of the value of the function. So 1/10 times our value times 5, which is the beginning water in the tank, gives us that much water in the tank. Excuse me. Let's try at time t, there's 20 centimeters of water in the tank. So after 1/10 of a second, the height of the water increases by 1.4355 centimeters. So we have an equation that's usable. For what? It's questionable, but it's usable. So let's take the method that we're doing. Like I said, we have time beginning, okay, an increment of 1/10 of a second, and let's try to tighten up that time to see if we can find a value where a is going to be equal to 1. All right. For the second tank, calculate the average change in the height, h2. We're still doing the same increment of 1/10 of a second, and express the answer as a number times the value of the original function time t. Okay, this is what we just did in the last one. Remember, we had the number times h1 of t, and then we'll explain it. So hold on a second. All right, like I said, I'm going to do less and less work each time I do one of these problems because you guys can see the pattern. So here I have my interval. Oh, I didn't want to do that. Sorry. I have the interval and the function I'm using. So plug it in, our rate of change function, h of 2 t plus 0.1 minus h of 2, h sub 2 evaluated at t over b minus a. So we just did h of 2 of b minus h of 2 of a over b minus a. Okay, you see the pattern. Everything I did with the last one here with exponents, if they're added, I'm really multiplying them. Factor out 3 to the t. I have 3 to the 0.1 minus 1 divided by 1. This right here I can calculate, which I did in my calculator, and got 1.16123. And then h of 2, h sub 2 of t equals 3 to the t. So I substituted, and we have our answer right there. So for the tank that is tripling every second, that's our function. So on average, over the time interval of 1/10 of a second, the water in tank 2 rises at a rate of approximately 1.16123 times h sub 2 of t, centimeters per second. Okay? Okay, let's make our time interval a little bit tighter. For each tank, calculate the average change in height from time t seconds to t plus 001 second. Express the answer as a number times the value of the original function time t, and then explain the meaning of these findings. Okay, hold on. So here you see I've calculated it between the time interval of t and t plus 100th of a second? No, thousandth of a second. So what you see here for this first one, my final equation is on average over time interval between t and t plus 0.001, the water in tank 1 rises at a rate of approximately 0.69339 times h sub 1 of t, centimeters per second. Okay, then I did tank 2, which triples, and there is my equation. So 1.09922 H2, so tank 2 as a function of time, centimeters per second. Okay? So we see here, on average, over time interval, the water in tank 1 rises approximately that, and then the water of tank 2 is approximately this one. I don't know why I didn't type it in again.
Okay, now what are we doing with this information, right? Well, I'll tell you. Oh, there's tank 2. Sorry. So we have both of the, oh, for goodness sakes, yeah, I'm not going to change it. We have both of the equations on the previous page. So both H1, tank 1, and tank 2 are on previous page. Sorry about that. All right, so now we're going to get into the actual discovery of E, Euler's number. If we look at, and remember I said that we're going to keep on taking more intricate slices of time. We're going to tighten the constraints, tighten them further in, and in, so that we can try to get that A term to be 1. All right, so if we look at the time interval between t and 1/10 of a second, these were our equations. And I apologize, that should be a sub 1, and that should be a sub 2. H sub 1 of t, H sub 2 of t. Sorry about that. So those are our two equations. I went ahead and calculated a 100th of a second. Let me put those there. Hold on. So what we see here, I've got the time interval of 1/10 of a second. Then I went ahead and calculated a 100th of a second. So this should have a little h sub 1 of t behind it, h sub 2 of t, and then the 1,000th of a second, which we just finished, h sub 1 of t, h sub 2 of t. Okay? So if the height of the water doubles, then the expression for the average rate of change contains a factor less than 1. Okay? That is, so doubles, that would be this equation, and this equation, and this equation, right? That's the doubles. The expression for the average rate of change contains a factor of less than 1. Our factors are 0.717, 735, 0.69, etc., and 0.69, etc. If the height of the water triples, then the expression for the average rate of change contains a factor greater than 1. Let me get a different color here. We'll show you that. Purple's a good color. So here we're tripling, we're greater than 1. Remember, we're trying to zero in on 1. Under what conditions does the expression for the average rate of change contain a factor of exactly 1? That's where E comes in. So when we get to exactly 1, that means that we're going to find Euler's number. All right, let me show you how. So in exercise 5, the average rate of change of the height of water in tank 1 for this interval can be described by the expression C1 2 to the t. And then tank 2 can be described as C2 3 to the t. What are the approximate values of C1 and C2? Okay, well, we have C1 is approximately, you guys have all seen this number, it's on the previous slide, 339, and then C2 is approximately 1.09922. Okay, remember we're doing 5 decimal places just because. So that's our answer there. Now we're going to use it. For some reason, I didn't make a slide for this next one, or the next few, so this is what we're doing. So number 7 says, as an experiment, let's look for a value of B. B is our base, right? So that if the height of the water can be described by h of t equals b to the t. So we're no longer doing 2 to the t or 3 to the t. We're doing b to the t. How many times am I going to mess around with that? Okay, b to the t. Then the expression for the average rate of change on the interval t to t plus 100th of a second is 1 times h of t. Okay, that's what we're going for. So let's write out the expression. H sub b t plus 0.001 minus h of b t over t plus 0.001 minus t. All right, I'm going to simplify that just a little bit. So we have h of b t times h, nope, sorry, we're not going to simplify it that much yet. So let's just keep it at h of b t plus 0.001 minus h of b t over 0.001, because remember, those cancel out and you're left with that. So let's keep this equation for the next slide. All right, set your equation that we just wrote equal to 1 times h of t. So I have h of b t plus 0.001 minus h of b of t over 0.001 equals 1 times h of b t. So we know that h of b is b to the t. H to b. Okay, that was said in the previous slide, so let's go ahead and replace it. B to the t plus 0.001. I've done this algebra step a few times, but we're going to do it one more time. Over 0.001 equals b to the t. So we have, and that should be t. I'm going to factor that b to the t out. Because remember, when we add exponents, it's like multiplying. Minus 1 all over 0.001 equals b to the t. Now I can divide both sides by b to the t and multiply both sides by 0.001. So I have b to the 0.001 minus 1 equals 0.001. Add 1 to both sides. B to the 0.001 equals 1.001, right? So that is where I stand. Okay? If that confused you, go look through it one more time and see if it makes sense. If not, we can chat a little bit about it tomorrow. Make a note, star it, right? All right, now we want to find the value of b that satisfies the equation you found in part B. But we do not have a way to explicitly solve this equation. Look back to exercise 6. Which two consecutive integers have b between them? So the equation we ended up with was b to the 0.001 equals 1.001. Okay, we don't know how to solve for this yet. Okay, we haven't been there, we haven't learned it. We're looking at constant 1, which is 0.69339, and constant 2, which is 1.09922. Okay, so somewhere in between those two values, we're looking for the base of the exponent, right there, that produces a rate of change on a really small interval near t that equals 1 times h of t. When that base is 2, the value of the rate is roughly 0.69339 times h of t. When the base is 3, the value of the rate is approximately 1.1. So we're somewhere between 0.69 and 1.1. So we're at 0.69 and 1.1. That's the range that we're in between. Okay? So the base we're looking for is somewhere between 2 and 3. Right here. This base is somewhere between 2 and 3. All right? So let's look at it. We're going to use our calculator to find an approximate value of b to 2 decimal places. So we're looking for b. And then, so we're going to plug in values of b and then raise them to 0.01. All right? And we're looking for a value of b that is close to 1. We're looking for where what we're looking for is where this is approximately 1, as close to 1 as possible. All right, so what I did, I set up a table in my calculator. Oh, for goodness sakes, I'm out of space already. Hold on, I'm going to move all this stuff up, okay? All right, if you look at this, I did it in my calculator. I typed in y equals b raised to the 0.001, and I changed my table set to go in increments of 0.1. And I just did a screenshot of the middle, because right here, if you see, I'm increasing. I get to 1.01 somewhere in here, and then it gets too high. Okay, I've overshot what it is. So my answer is somewhere in this value, okay, between 2.6 and 2.8. So the next thing I need to do is I need to make my table set just a little bit tighter. So for my B's, I'm going to start at I'm just going to start at 2.7, because I think it's somewhere in the middle there. 2.71, 2.72, 2.73, 2.74. I'm going to plug that in for B and get my values. So 2.71, I get 1, and my significant figures doesn't go high enough in my calculator, so I had to do this one by hand. 0.00997. 2.72, I have 1.001001. 2.73, 1.001005. So again, I've increased, which is good, but then I surpassed. So in essence, I don't want that one or that one. This is what I'm going for. Okay? So B is approximately 2.72. So remember what we're doing here. We're taking tighter and tighter slices of time to try to get that A value as close to 1 as possible in our exponential function. All right? So let me show you how it works. I know, the longest lesson ever, right? So your part 8, or number 8 says this, and then we're just about done. Okay, verify for the value of B found in exercise 7 in that equation where h of b equals b to the t. So let's plug everything in and see how it works. H of b, this is the equation we started out with a few slides ago. All over, I'm saving a step there, right? So we know that we have a value of b equals 2.72, or approximately 2.72. Okay, so this equation changed to b to the t plus 0.001 minus b to the t all over 0.001, right? We know b is approximately 2.72 to the t times 2.72 to the 0.001 minus 2.72 to the t, all over 0.001. I'm going to factor that out. 2.72 to the t times 2.72 to the 0.001 minus 1 over 0.001. Need more space. So if you crunch, that should be a 0. If you crunch this right here, you get 1. Okay, oops, sorry about that. So we're left with 1.00 times 2.72 to the t. Okay, 1.00 times h of b to the t. So to get this to 1, my base has to be approximately 2.72. And let's just be a little more accurate because it's important. Approximately 2.72. When the height of the water increases by a factor of 2.72, not by a factor of 2, not by a factor of 3, somewhere in between. So when the height of the water increases by a factor of 2.72 units per second, the height at any time is equal to the rate of change of the height at that time. All right, that's the goal. I'm going to say it again. When the height of the water increases by a factor of 2.72 units per second, the height at any time is equal to the rate of change of the height at that time. We just found Euler's number. Okay, this right here, 2.72, is E. If you find your calculator, there's an E there. If you press it and push enter, you'll get 2.718281828. And it goes on forever and ever and ever and ever and ever. All right? It's an irrational number. So it can't accurately be represented by a decimal. All right? And that's it. That's E. We're going to play with it in our problem set, and it's a lot of fun. But we need it to do logarithms and exponential functions, so that's why we did it. Phew.